let's look at this new section, 3.2, on implicit differentiation. This is going to deal with when you have different variables than what we're taking the derivative with respect to. Most of the time we take the derivative with respect to x, like dy dx, change in y over change in x. But later on we'll be talking about like change in time, dr dt, change in the radius over time, dv dt, change in velocity over time. So there are different things we take the derivative with respect to, and if the letter you're taking the derivative of and is different than the one you're taking it with respect to, we have to realize that's the chain rule in its purest form. All right, so let's see what's going on today. So we've got distinguish between functions written in implicit form and explicit form. Use implicit differentiation to find the derivative of a function. All right, an implicit function is a function written where y is not isolated. Some implicit functions can be written in explicit form, like x times y equals 1. You can certainly solve for y, isolate the y, and do y equals 1 over x, while others cannot, like 2y squared plus 3xy is equal to 3. You can certainly factor out a y, but you'll never be able to isolate the y, so it just can't be done. So that would be an explicit form. Implicit. I already got it mixed up. Functions that cannot be written explicitly must apply implicit differentiation. So again, as everything we do in here, if you can do it another way, do it. So if you can change it to an explicit form, like pretty much everything we've done so far, because everything is y equals or f of x equals, then we can just go ahead and apply the derivatives that we know and we're done. But if you can't, we have to use the implicit differentiation utilizing the chain rule. So here we go. When differentiating with respect to x, any term with only x variables will be differentiated normally. Any term with a y or another variable, not x, must be differentiated using the chain rule. So I'll write that down. Chain rule. Because it is assumed that y is defined implicitly as a differentiable function of x. So you'll get used to it as we do them, but I just wanted to make that clear early on that if it's not x, we have to apply the chain rule. If it is x, then plain old derivative applies, and I'll tell you why in a minute, why it doesn't matter if we continue with the chain rule with the x. So here's a great example right here. So I want the derivative of x cubed. We already know that. Power rule, 3 times x squared. Now here's why we don't need to apply the chain rule. The chain rule would imply dx dx. Well, what's dx? What's the change in x with respect to itself? Well, even common sense says dx over dx is 1. That will always be 1. That's why it's just a waste of your time to worry about taking something with respect to the same letter you have and worrying about the chain rule. So the answer is just 3x squared. That's it. Let's look at a second one. So this one's different. This one's the derivative with respect to x of y cubed. How is y changing with respect to x? Don't know. We need some help. So we can just take the derivative. That doesn't change. It's still going to be 3y squared. But the chain rule says now take the derivative of y, and in this case, using Leibniz notation, dy dx. That could also be written as times y prime, right? The change in y. So either using Newton's form or Leibniz form. I prefer Leibniz form in this case. I have had students in the past use y prime, and it works just fine. You can still find the answer that way. So this answer is now that. If you left off the dy dx, you would not have the complete answer because we need to know what the chain implies, which is the dy dx. There we go. Let's look at the third one. Here's what I was talking about earlier. Now we have, let's say that's velocity or volume, or probably velocity. So the derivative with respect to time of, sorry, I keep bumping this thing. Get it back in a second. The derivative with respect to time of velocity, here we go, is going to be, well, the derivative of v, sorry, I'm waiting for it to come back. Come on. Okay. The derivative of v is just 1. That's no big deal. Times dv dt. And we really don't need the 1. So it would just be dv dt. And that makes sense because we're just looking at velocity with respect to time as dv dt. So that makes sense. So we start talking about some other problems using implicit differentiation. This will be a case where you're doing the change in volume over time, or sorry, velocity over time. Could be volume, I don't know. All right, so that's example 3. So those are pretty basic. Let's see where this goes. The process doesn't get any fancier. It just sometimes gets more intense as far as more parts all moving at once. So we have those 3. All right, let's try this one. So now I've got derivative with respect to x of x plus 3y. Well, the derivative of x is 1. And again, we're not going to waste dx dx, so that part's done. Plus 3 times dy dx. And we're done. Right now, it feels like we're really not doing anything except just addressing the chain. Where this is going to come into play is if we then go try to solve for dy dx, which will be the overall change of y with respect to x, the overall derivative. So let's get to that eventually. We're just not there yet because these don't equal anything. That's the problem. All right, number 4. Looks like 4 is going to bring in a product rule. So that's going to be the derivative of x, which is 1, times y squared plus, we can dump the 1 in a minute, x times, what's the derivative of y squared? Simply 2y. But that's a y, not an x, so we got to think about dy dx. And the only thing I could do, and I will, why not, is y squared plus x, let's do 2xy, really doesn't matter, dy dx. Again, this, even with the 1 in it, would have been fine. And there's the second one. Either one are acceptable. And that's it. So that's the implicit differentiation where we have to deal with variables that don't match what we're trying to find the derivative with respect to. That's a lot of words. Okay, that's number 4. All right, let's see where this goes from here. So here are the steps that we're going to use in the process. We've already started using the process. We just haven't made a plan on how to approach one where we're actually going to find dy dx. So this says differentiate, oh, I guess it's just not going to straighten out. Let's try that. There we go. Differentiate both sides of the equation. Now we're going to have it equal to something. It's going to be a full equation. We're going to take the derivative of the left and the right with respect to x, if that's what it is. All these are most likely going to be with x. Collect all terms involving dy dx on the left side of the equation and move all other terms to the right side. Factor the dy dx out of the left side of the equation. So now you just have a dy dx times some group of terms. And then we just go ahead and solve for dy dx just by getting rid of those terms by dividing by that whole chunk. Because if you've got the dy dx factored out, you can take the factor and divide it on both sides and you'll have dy dx. What does that mean? That means we will know the change in y with respect to x, which is the derivative. We can find tangent, we can find all kinds of changes based on the original implicit form. We couldn't do anything with it until it was dy dx. And now it's going to look a lot more like what we've been doing all along. So let's look at an example. Find the equation for the slope of the line. Okay. So we just want the equation. We won't be able to find the slope because we don't know what x or y are. But we're just going to go for this. So the first thing I'm going to do is I'm going to go ahead and put a big parentheses around the whole thing. I always want to remind myself to do this. D dx. Let's write that a lot better. D dx. So the derivative of this whole thing with respect to x. I'm always remembering what the main focus is. It's with respect to x. So that would be our first issue is 3y squared, dy dx. There's our first one. Plus, what's our second term? Well, that would be 2y times y is different than x, so that would be times the chain rule, dy dx. Minus 5 times, again, dy dx. And now we've got minus 2x. Do I need dx dx? No, that's not needed. And then don't forget this part. This is a nice little bonus. Anything that's a constant, its derivative is 0. So I'm thinking about gathering all my dy dx's together, push the 2x to the right. So let's see where that goes. I've got plenty of room, so I'm not going to skip any steps. Let's do this. Plus 2y dy dx minus 5 dy dx is equal to 2x. There we go. So now we've got all the dy dx's gathered. We can go ahead and factor out a dy dx because that's what we want to solve for. And all would be left is 3y squared plus 2y minus 5 is equal to 2x. I think you can see the last step already. Dy dx would just be dividing each side by that 3y squared plus 2y minus 5, and that would be 2x over 3y squared plus 2y minus 5. Now that looks pretty fancy, but if you think about it, if I were to tell you the point was like 1, 1, you could find the slope at 1, 1, even with this crazy implicit function, implicit differentiation we did. Put in 1 for x, 1 for y, and what would that be? 2 over 0. Ooh, that's a bad example. That'd be undefined. Don't do that. Try 2, 2. So if you did 2, you'd have 4 on top. You'd have 12 plus 4, 16, 11. So you'd have 4 elevenths. So at 2, 2, the slope would be 4 elevenths. So it's interesting how the more we learn, the more we can do. And there's nothing holding us back anymore, even on random crazy functions that we can't even put in our graphing calculator. Only Desmos could handle that calculator, that form. So now we know. Interesting. I didn't want to go too deep into that. We'll get to that, I promise. Let's go to number 2. So we start with a little product rule here, but remember the chain whenever you're dealing with a variable different than the one we're trying to do with respect to. And that is dx. All right, so the derivative of x cubed is 3x squared, no issues there, times y cubed, that's part of the product rule, we don't have to do anything to it, and then plus x cubed times 3y squared dy dx. Cool. Minus 1, I don't need a 1, dy dx is equal to 1. Because the derivative of x is 1 dx dx, again, don't need it. So I'm going to gather, all I need to do is push this guy over, and I'm going to have x cubed, let's put a 3 in front, start to organize a little bit, 3x cubed y squared dy dx minus dy dx is equal to 1 subtract that entire first term, since it wasn't a dy dx term. And now we've got our two sides separated. And now I can take a dy dx and factor that out. And all I'll have left is 3x cubed y squared minus 1. And on the right side, 1 minus 3x squared y cubed. And finally, our last step is to divide by the factor. And we'll have dy dx is equal to 1 minus 3x squared y cubed all over 3x cubed y squared minus 1. That is our final equation for the slope, for the derivative, for the change in y with respect to x. And all we would need after this point, we just have a general form right now. All we would need at this point is whatever x and y were, we could then find the slope at that actual point. So there we go. Let's see what we have next. Number 2, let's look at the next example, which is going to be this guy. So now we've got some numbers to plug in. I'm going to teach you a little trick here. I really feel like you don't want to let the algebra take over the calculus. You're going to hear me say that a lot this year, because I really want to focus on learning new things, not doubling back and rehashing on things we've done for years. So we don't worry about simplifying. We don't worry about, going through long processes of the things you used to do, because we're trying to discover the calculus. We're trying to see exactly where this is going. So I've got this implicit function. We see that it is determine the slope of the graph. 3 times x squared plus y squared all squared is equal to 100xy. We're certainly not isolating a y anytime soon. And we're going to check it at the point 3, 1. So let me show you something I would do here. We're still going to do it the same way. I didn't have space to write next to it, so I'm just going to do this. d dx of this whole function. 3 times x squared plus y squared squared. And then, let's see, did I do that okay? There we go. Is equal to, oh, I should probably not do it that way. is, come on back. Okay, I'll go back here. Okay, squared, all right, is equal to 100xy. And I'm using that d dx around the entire equation. So sorry about that confusion at first. So we now have this thing set up. So the first rule is take the derivative of the left and the right. So what do we got there? Looks to me like we have a 3 times 2, so that's be 6 times x squared plus y squared to the first, which we don't need to write, times the derivative of the inside. Well, what's the inside? Well, the inside is 2x, no need for a chain, it's x, plus 2y dy dx. Great, because you got to have the chain. And that's the left side. We're done. On the right side, we have the product rule. Let's see if I can give ourselves a little more space. On the right side, we have the product rule, and that's going to be 100 times y. That would be your first step, because you took the derivative of 100x, which is just 100, no chain, times y left alone, plus 100x times the derivative of y, which is dy dx. There we go. Now here's where the part comes in where I can save you some troubles. If you have a bunch of dy dx's and x's and y's, and you're trying to get them isolated, those dy dx's, and there's one inside a function you've got to distribute and all that stuff, I would really recommend this is when, and there's no rules about this, but I recommend plugging in the 3 and the 1 now. So if you plug it in now, substitute 3, 1 now. Don't wait. All right, so we plug in 3, 1 now. We'll have 6 times. Well, that would be 3 squared plus 1 squared, and then times 2 times 3 plus 2 times 1 times dy dx. So now you can see the only variable you'll have is dy dx. A little bit nicer to work with now that we have variables available. 100 times y, which is 1, and then 100 times 3. Could I sneak it in? dy dx. There we go. So now it's going to be a lot cleaner. It's a bunch of whole numbers, and we don't have any craziness going on. So inside this parentheses, we're looking at what? 9 tenths, that's 60. And inside this bracket, we have 6 plus 2 dy dx. And on the right side, we have what? 100 plus 300 dy dx. And now all we have to do is get the dy dx's together. Looks like it would be pretty easy to bring the 300 to the left, but let's go ahead and distribute first. That'd be what? 360 plus 120 dy dx is equal to 100 plus 300 dy dx. And now it's just like moving furniture, people. I'm just going to move things around. I'm going to move the dy dx's to the left, the 360 to the right. And what is that? If I bring the 300 over, that's subtracting 300, that'd be what? Negative 180. Negative 180 dy dx is equal to, subtracting 360 would be negative 260. And you can see the very next step is just dy dx. This will be our derivative, our actual slope. Why is this not wanting to write? dy dx is equal to, well, that would be 260, 2 negatives make a positive, so I'll dump the negative, over 180, dump the zeros, cut it in half, 13 over 9. So our actual slope at that point would be 13 over 9. Sorry if I'm underneath my picture right now, but that's all it is, 13 ninths. I'll move it in a second. How about, oh, there we go. So we'd have 13 ninths as our derivative. So that's a nice little thing you can do following the same process. As soon as I'm plugging in points, I do it right away. You can certainly go through and solve for dy dx if you feel, and then plug in the numbers. You'd still get the same thing. I just think that's a lot cleaner on the algebra side, so just a suggestion. So let's look at the last one. Here we go. Find the second derivative of the function 4xy is equal to 10. Sorry about my iPad. Here we go. Okay. So I want to rewrite that again because they didn't leave me enough space. So d dx of 4xy is equal to 10. So the derivative looks like product rule on the left. That's just going to be 4 times y plus 4x times dy dx, and that's going to equal 0, right? Because the derivative of 10 is 0. Nice. So I can go ahead and get the dy dx isolated pretty quickly. 4x dy dx is equal to negative 4y. Divide both sides by 4x. I usually don't show that, but why not? It was easy. Dy dx is equal to, I can divide both by 4, so it'd be negative y over x. So save that. I'm going to show you why in a minute. Save that, because that has to be done. We don't have a choice. In order to get to a second derivative, as we've seen so far, you always have to go through the first derivative. So we found the velocity, we found the first derivative. Now we're going to proceed to the second derivative, or like acceleration. All right, so how do I find the second derivative? Well, I take the derivative of the original derivative. So that's going to be dy dx is equal to negative y over x. So I am going to take d dx of that. So the derivative of y with respect to x as a second derivative is just like this. This is Leibniz notation. D squared y over dx squared. You'll get used to it. We'll use it a bunch. Is equal to, looks to me like the right side is going to be a quotient rule. Now we only need to keep that blue box off to the left there. I don't need the rest of this problem right now. So I'm just going to give myself more space right here. Okay, low d high, right? Low. Well, what's the derivative of the high? Well, the derivative of negative y is negative 1, which I don't need, but it's dy dx, and it's negative. There we go, done. Minus high, d low, which is 1. Really don't need to write it, but why not? It's there. Over the square of what's below, which is x squared. Okay, so if I do that, you'd think I'm done, but I'm really not. Something's weird here. I have a variable that I haven't addressed. X and y, I can plug in points. Well, what's negative dy dx? Well, if you recall, I told you to pay attention to the first step we took, and that was this bad boy. Dy dx is negative y over x. Okay, and this will happen every time, guys, because the chain rule is going to bring back dy dx when you do the second derivative. So just be ready for it. Don't be surprised when it does. That'll be d squared y over dx squared is equal to, well, I'm just going to plug it in, x times. Well, I want opposite of it, so now it's just going to be y over x. There we go. And minus negatives, I just call that plus y, all over x squared. Well, I could stop there. I have no problem stopping there, but my gosh, look at this, guys. The x is going to cancel, and y plus y is 2y. Come on, let's finish it. D squared y over dx squared is just going to be 2y over x squared, and I believe we nailed it. So that is the second derivative of our original function at whatever point you want to plug in. And once again, if you want to plug in 5, 6, the answer would be 12 over 25. That would be the slope. And that would be the second derivative. That would be the change in the first derivative. We'll get into that later as we go. So that's it for today. Check out the assignment online. If you have any questions, come see me. This is good stuff. We're getting more and more in our toolbox, so we can do so many more problems that won't hold us back and say, oh, but we can't do those. We can do a lot of stuff. Now we can do explicit. We've already done that. And now we've introduced implicit functions with different variables. All right. Have a good day.